Right, so what I'm going to be taking you through the second session now is how to analyze survey data where one has used these verbal ordinal scales. Now, verbal ordinal scales come in different forms. The classic one is the so-called Likert or Likert scale. But then you get scales of importance, you get scales of satisfaction, you get all sorts of different scales that can be used. And sort of generically, I refer to them as verbal ordinal scales because they are verbal scales. They're not numeric scales. Even if we use numbers to code the results, they're actually verbal scales. And they're ordinal in the sense of if we're looking for, at a scale of agreement, we go from sort of strongly disagree, neither agree nor disagree, and there's a sequence associated with them or an order associated with them. Now, I'm sure you're familiar with those. You do the lecture evaluations using that sort of scale. Any marketing research is almost certainly going to have those sorts of scales. And the conventional way of analyzing those is to assume that they are actually numeric, even if they're not. All right, so to simply assign a numeric value to each of those particular categories of response. But I'll show you in a moment that in fact that's a very unreliable way of analyzing the data, and I mentioned that earlier, I think. So what I'm going to show you is a way of analyzing it that actually is reliable and that doesn't make the fundamentally flawed assumptions that go along with assuming it to be numeric. Now, the interesting thing is that and it's a bit of a digression, but there was an article that was published by Leibovitz in 1970 where he spoke about being able to assign numeric values to what are effectively just ordinal data. And people have quoted Leibovitz over the years as justification for making that assumption that you can assign these numeric values. But the interesting thing is that in his paper, Leibovitz actually made this statement here that although his findings were that you can probably do it quite reliably, if you look at the second half there, the more conservative procedure is to treat ordinal data as strictly ordinal and not numeric, and thereby avoid the possibility of attributing a numeric property to a verbal scale. And people have tended to ignore that. Now, what's interesting about that is we've spoken, I think, in the past, and Terry probably spoke to you some months ago about how you need to go back to the original sources. All right? So you don't want to read something in an article about what some other author said. You want to go back to the original. Because depending on which part of Leibovitz an author has cited, you're going to get a fundamentally different message. And that's why it's important to actually go back to the original work. And rather than depending on what the person has, what the intermediary has reported. So what I'm doing in this case is I'm actually exploring that possibility or that caveat that Leibovitz has mentioned here, that the more conservative approach is to treat ordinal data as purely ordinal. Now, you might see in some of the literature, and certainly if you go into the library and you look at research that was done here in the late 1990s and early 2000s, you'll see people referring to some work done by Mike Ben-Dixon and Merle Sandler in 1995. It was published in 1995, where he used a technique called correspondence analysis to rescale the ordinal data into numeric data. Now, it turns out that particular technique doesn't work particularly well under all circumstances. And so what I'm going to show you is actually supersedes that work, or the 1995 work. So Mike Ben-Dixon, he was my predecessor here, and then I wrote the article in 2005, which then showed that his method was unreliable. That's the way academia works. Okay? And Mike Ben-Dixon was actually one of the blind reviewers of my paper that I published in 2005. So, as I said, it's a bit incestuous at times, but that's the way it works. So, what I'm going to show you then is an alternative, and is the one that is demonstrably more reliable and valid, and that's the paper that I published in 2005 was addressing that issue of reliability and validity. Just to recap then a little bit on what I was saying to you about last session about when we take a sample of data and we're extrapolating it to a population. So I've just shown this a little bit differently here, where the inferential approach to statistics, so-called inferential statistics, we gather a sample of data and we analyze the sample of data on the understanding that that sample is representative. So when we work out things like the means, that standard deviations, regression models, that sort of thing, we then, by inference, we then draw conclusions about the population. So that's the process that we go through. So sample statistics make inferences about what the population statistics are. That's the normal process. Now, I just expand on that a little bit when we are looking at survey data. And if you think about your attitudes to something or your perceptions of something, your level of satisfaction with issues, the level of importance that you perceive, we don't think in boxes, all right? So we don't think in a 5-point scale, all right? Our brains are a bit more linear than that. So when I ask you to fill in a survey, or when you ask somebody to fill in a survey, what you're actually asking them to do is to take that information that's in their head, or that opinion, and you're asking them to turn it into a discrete value of some sort. So within each category, you actually don't have only one view. Within the agree category of responses, you have a range of possible levels of agreement in terms of one's actual understanding and perceptions. Does that make sense? All right. It does. Good. And so what I'm saying is that we go through a process, an intellectual process of discretization, turning it from continuous into discrete. And I'm going to show you that that's going to introduce errors. And it's not because you make a mistake, but it's just because of the fact that we are changing from being a continuous scale into being a categorical scale. And so I'm going to focus on that particular box there, the transformation box. Okay, so what happens intellectually when we do that? So this discretization error that comes in, it comes about as a result of this transformation from a continuous to ordinal level data, and I have literally never seen it categorized in the literature, or addressed in the literature. So it's usually ignored. Now, a student here at the business school doing his MBA research report looked at some published research and was able to demonstrate that some published peer review research has actually come up with the wrong answers because they analyzed it incorrectly. So it's not insignificant, it's not immaterial, the fact that you get the wrong answers sometimes if you analyze it incorrectly. Okay, so we need to just keep that in the back of your mind. So really what I'm saying here is that as I'm trying to illustrate in this slide sort of an opinion going from very negative or very much on the one side through to very much on the other side. This process of transformation involves a number of threshold values where if you really, really disagree with something, if I'm assuming that that's a Likert scale, then you're going to answer it in this category. But as you disagree less, there will come a threshold where you'll no longer tick that box or press that button on an online survey. You'll now put your answer in that category. And so each of these categories is separated by a different threshold. Does that make sense?
Yeah.
Okay. So what I'm going to do, that's just the mathematical statement of it. What I'm showing you in this slide here is that merely by doing that, if I had a population with a mean of 0 and a standard deviation of 1, and I analyzed that data after it had gone through this transformation, this turning it into a discrete value, we actually get an error. We get a mean of 0, that's fine, but a standard deviation not of 1, but of 1.018. Now you might think, well, that's pretty insignificant and not a big deal. The problem is that in other circumstances, depending on the average and the standard deviation, you might get much bigger errors. And there's another example. And in this case, the mean is 1 and the standard deviation is 1. And you see that these errors have now got to be quite big. And if those errors are large, that's when you're going to get results that are incorrect, because your hypothesis tests, whether it's t-tests or whether it's ANOVA tests, various different statistical tests, are largely based on means and standard deviations. Many of them are based on that. And so if your calculations are wrong, you're going to get the wrong results of your hypothesis tests. So this is not immaterial, is what I'm saying. And bear in mind, this is not because you've done anything wrong. It's not because of a biased sample or anything like that. It is merely because of categorizing into, in this case, 5 categories of response. Under different circumstances, the errors go all over the place. Here's an example where instead of a mean of 1, you get a mean of 0.66. So I'm quite different from what the true mean should be. This discretization error exists in any data where you have categorized or turned into a discrete value that continuous variable, and it does result in these incorrect research findings potentially. So what I'm going to do is I'm going to show you an alternative method, and the alternative method involves building a mathematical model. It's an Excel model, as it turns out, mathematical model that models the process of discretization. In other words, that categorization. So instead of going through this whole process of drawing a sample, working out the sample statistics per se, and then saying, right, well, the sample statistics are the same as the population statistics, we've seen that's wrong in this case, I propose a fundamentally different approach. And the approach is as follows. I build this Excel model. It's like a simulation model. If you don't follow this detail, doesn't matter. I want you to understand the principles of what I'm doing here. All right? That's all I'm wanting you to understand. Principles. What we do is that analog. That's what I'm talking about. That's an Excel model. And in that Excel model, I'm going to slice up exactly as we do with when we ask somebody to fill in a survey. I'll slice up the distribution of opinion. And in the same way that I get a certain number of people answering in a certain number, the different categories, in my model, I'm going to get these, I call them synthesized proportions. They're in the Excel model. It's just a mathematical equation. Having created that model, it's got certain inputs or certain parameters, means, standard deviations, and that sort of thing. Now, I don't know what those are. I can just set them arbitrarily. And therefore, if I compare my actual survey data, which is this area of this diagram here, with my mathematical model, they're going to be different. Clearly, there's going to be an error. There's going to be a difference between the two. But if I can eliminate the difference between the two, if I can eliminate the difference between my survey data, my actual responses to my questionnaire, and my mathematical model on Excel, if I can match the two, then I can say that this Excel model matches reality, because that's what I've got here. So if I can eliminate that error, or at least minimize it, then I've got something that closely matches reality. All right, does that in principle make some sense? And you see, it's not the same as working out the sample statistics and making the inference. It's actually creating a different type of model. So I'm going to talk you through how we do that in practice. And again, I'm only asking for understanding and conceptual understanding. It's not about the equations and the mathematics of it. The example is some research that was done by a previous student here at the business school. And the research was looking at the concept of corporate governance and people's perception of it, and specifically directors and executive and non-executive directors, their understanding of corporate governance. And there were multiple survey items, there were statements, and then the participants were expected to respond on a Likert scale, whether they agreed or disagreed, and how much on a 5-point scale. So that's the example that I'm going to be showing you. So having gathered the data, what do we find? We find we can tabulate for all of our questions in our survey, or all of our items in the survey. We could tabulate how many participants responded to each question strongly disagree, how many disagreed, how many neither agree nor disagree, and so on. So we just it's a cross tabulation. Okay, so that's the actual data coming out of the survey, and that's fixed, right? We can't change that, right? So that's that sort of left-hand column of the diagram. Now what I'm going to do is I'm going to arbitrarily say, well, let's guess a mean and a standard deviation for those items in my model. So I'm just going to assign arbitrary values. Normally I assign 0 and 1 just because that's kind of a convention. So I assign those to each of my questions. Each one has its own unique mean and standard deviation. Then, going back to those threshold values, remember I said that there were thresholds between each of the categories. Again, I simply say I'm going to assign some arbitrary values to those. And essentially what I'm doing there is I'm saying, if that's my scale, my continuous scale of attitude or perception, then what I'm going to do is I'm going to put in these threshold values, and anything falling within that category, I'm going to call that a strongly disagree. Anything falling within that category, I'll say as a disagree in my model, and so on. So I'm simply slicing up the range of opinion. So what we now do is we say, if we've now got these distributions of opinion and these thresholds, what I can do is I can calculate how many of my, or what proportion of my participants will answer in each category. So I can say that if that's my distribution of opinion, then I would expect that, based on that area, I'd expect a certain number of people to fall within that category. I'd expect a certain number of people to fall in that category, and so on. This is a normal distribution, a normal curve, bell curve. Okay, so I'm saying that based on that, I would expect a certain number of people in each of those categories.
Are you expecting us to have these type of distribution graphs in our paper?
No, I'm explaining conceptually. Okay, so I'm not expecting that. Not at all. Okay. So what I have then is, based on these calculations, it's just an Excel formula, then I would expect to get a certain number of responses in each of my categories. Now remember, I've got the actual observed ones that I got from my data set. This is now based on my Excel model. So based on that normal distribution, based on those thresholds, I expect a certain number of people to be in each of those. Now the issue is, are the observed numbers the same as the expected numbers? Well, they're probably not, because I've just guessed those initial values. So what I do is I calculate what's called the chi-squared value. Now a chi-squared value is calculated by looking at the difference between the two. And the actual formula is here, where we look at the observed number, in other words the actual data, minus the expected number, which has come from our calculations. We square it in order to make it all positive, and we divide it by the expected number in order to get the relative squared error. And we add it up across all of our cells, all of that whole table. So if the two data sets are very different, then we're going to get a big difference between the two. We'll square those, we'll get a big number of chi-squared. But if the two data sets are closer together, then those values will be smaller, and the chi-squared value will then be smaller. So chi-squared is a measure of the difference between my observed values and my Excel model. So all I need to do now is to change my Excel model until such time as my chi-squared value gets as small as possible.
But that's you just adjusting your Excel spreadsheet until you get
Correct.
it.
Yeah. All right. But remember that I'm adjusting my Excel spreadsheet. I'm not adjusting my data.
Yes,
Right.
no,
That's important.
You're trying to bring this.
I'm bringing my Excel model
manipulate.
in line with the actual data I've got. Okay. Some people say, aren't I fiddling with the data? And the answer is no, I'm not changing the data, the raw data that I got from my survey. I'm changing my model. But I'll show you that. Okay. So how do I do it? Well, remember that my means and my standard deviations of those distributions, I guessed those up front. So I can change those and see if I can fit the data that way. I can also change the threshold values. So that's what my data set looks like in Excel. This is, I'll actually show it to you running in a moment. So up there at the top we've got our actual observed frequencies. So that's what came out of our data. Then I've got my expected frequencies. So there's a whole lot of Excel formulae in there based on the normal distribution. There are the chi-squared values for each of the cells adding up to, that's actually 933. Is the total chi-squared. And notice that all of my means and standard deviations are 0 and 1 respectively, and I've just got arbitrary values here for my thresholds. So what I'm going to do now is I'm going to see whether I can minimize that chi-squared by changing the parameters that I put in as arbitrary values. All right. Okay, so let me just switch over to Excel now. This is on Sakai, so you've got access to this. And what you see, it's exactly the same set of numbers, it's just slightly differently laid out. So you've got the observed frequencies at the top, you've got the expected frequencies, you've got the means and standard deviations there, and so on. And there you'll see the 933 of the chi-square. Now there's a very nice tool that we can use to minimize chi-squared. Does anybody know what, anybody got thoughts on what it is? Chanel? Well, it works on the basis of calculus, differential calculus, but actually in Excel, there's a tool that does it for us. Sorry? Solver. All right, Solver is an add-in. It's part of the Excel package. You don't have to purchase it. You might have to activate it just by going into your options menu. But what Solver enables you to do... Say Solver then allows GoalSeek will enable you to get to a particular value based on one target cell, one variable and one target cell. Solver enables you to look at one target cell with multiple input variables. Okay, so if I go in here, the objective cell, you can see there, it's probably a bit small. There you can see it's highlighting my chi-squared value, so it's set up there so that chi-squared value will be set to a minimum by changing my means and my standard deviations. Now what you're going to need to do is you need to watch this quite carefully because it runs very quickly. I'm going to press solve, and down the bottom left hand corner here you will actually see the algorithm running. You'll actually see the chi-squared value. Remember that it's starting off at 933, and you will see it minimizing through successive trials and errors you referred to. But it's actually an algorithmic process that it searches for it, similar to differentiation. So it, as I said, runs pretty quickly. So there I press solve, there it goes, right? 134, 130, 128. And it has now optimized those two models. Right? Sorry, it's optimized the model with the raw data. Okay, so what I will do for you is I will give you the spreadsheet, all right? Or you can send me your data, and it'll take me 2 minutes to put the numbers in. I mean, literally, it's the observed frequencies. It's just a count equals count if in the formula, and we can run that, and you can see it takes 10 seconds to run it. So I can do that for you. Yeah. Of course.
It won't help if you can't analyze it or explain it.
Right, so that's what we're about to talk about now, is the explanation. Okay, so we're about to talk about exactly what that means. All right. But the fact is it takes that long only to analyze, which is quite nice. Yep.
It just says standard deviation on its own in the mean.
So there's three things that, we'll look at that in a moment. I'm going to show you graphically what's happened there. So I'm just going to show you now. Okay, guys, just settle, please. I'm going to show you now graphically what happened in those few seconds there. All right. So I've taken two examples out of that survey. The first example is a statement that says Internal Audit Department used excessively to champion corporate governance. And notice those are the responses that were received. Actual. Yeah, actual responses. All right. Second one, corporate governance understood as a continuous process, not an event or program. All right, and they're the responses that were received. Now, somebody asked is how would you present that, or would you present this data in your report? This is how you might present the results. Okay, now notice that what I've done is I've done it in such a way that they are discrete. So that it's not a continuous chart because they are distinct categories. So that's important because that's the raw data. And if you look at the one on the left, it looks like it's bimodal. You can see that the sort of middle category is smaller and they've got two peaks. So it certainly doesn't look like a normal distribution. And this one on the right-hand side here looks pretty skewed. And again, it really doesn't look much like a normal distribution. So you might ask the question, how on earth can I fit a normal distribution to those? Well, what I do is as follows. I redraw that. So this is what the model looks like when I start. In other words, before the optimization process. So notice that the two blue distributions are the same. They've got a mean of 0, standard deviation of 1. Those are the arbitrary values that I assigned. I've changed this into a continuous distribution, all right, the red distribution. So I'm joining them up now. But it's pretty clear that they don't fit, do they? I mean, there's a big difference here. There's a difference, there's a difference, there's a difference, there's a difference. Similarly here, there's a big difference here, big difference there. So clearly I'm not fitting. But what happens when I tell the solver to run is as follows. So I want you to look out for what changes as we go through the animation. And it'll rerun over and over again. You should see 3 things changing in the process.
See your mark going down from 8 to 6.
So as we're going through it, the red chart, the areas of those boxes represent the number of people that have responded in each category. So it's not the height, it's the area. Area represents the distribution there. So what do you see happening? What are the things that are changing as we go through the algorithm, the distribution fitting algorithm? Because that's what this is called.
Standard deviation is changing.
Right. So when you say the standard deviation, you're talking about the spread. Okay. So we see this one, the standard deviation is getting smaller. So the spread it's getting narrower. This one, standard deviation is getting broader. So quite correct. Standard deviation is changing. What else is changing? The graph. What on the graph is there changing? The height of the graph. Right now, the height of the graph is related to the spread because the area stays constant. The area under the curve is in fact identical to the area under the total of the boxes. The areas stay constant. So obviously as it gets wider, it's got to get flatter. So that's really the same thing. Something else is happening to the blue line, the blue distribution. Right. Well, you're saying the median. In fact, it's the mean, all right? But it is the same thing. Yeah. So what we see on this one, the mean. Guys, please. Sorry. What you see on the left-hand side is that the mean is going negative. It's actually shifting. The curve is shifting to the left. On this one, the curve is shifting to the right. The mean is going positive. So we see that the mean is changing and the standard deviation is changing. But what else is changing to reach that point at the end of the algorithm, where now what we see is that we actually have a reasonably good fit between the red curve, which is our raw data, our observed data, and our blue lines, which is the distribution that we've fitted. So what's the third thing that's changed from what I originally had? Okay, let's just... Okay, so it's starting at that point. Oops, sorry. It starts at that point there. In fact, let's go up there. That's where it starts. Okay? That's where it ends. Right, so certainly the fit is better, absolutely. And that we certainly see that, but how have we achieved that better fit?
So by itself adjusting the mean and the standard deviation, it's kind of forced or adjusted the number of answers per category.
That's correct. But something else has happened. What's happened to the red one?
The red one.
The red has also changed shape. It's not only the blue that's changed shape, the red lines have also changed shape.
The one that says neither, if I'm not mistaken, on this side.
Yeah.
Became thinner and longer.
Right.
So,
Okay.
Yeah.
So what has changed to make it thinner and longer? All right. Those thresholds between the categories have changed. You see, that's what's actually happened. So we started off with thresholds that were equally spaced, all right, because that was our assumption, remember? Okay, if we go back to the 1, 2, 3, 4, 5, we were assuming that they're equally spaced. The reality is that they're not, and that shows it. So what we're seeing here is, in fact, if we look at the agree category, agree is a very wide category. What that means is that the range of perceptions that are classified as agree is quite broad. The range of attitudes or perceptions classified as neither is quite narrow. So what we did is the algorithm changed the thresholds until we got the best fit possible. Okay. And to answer your question, if I go back to my Excel worksheet, there's a value that I can look at across here where I can check to see whether that value there tells me that it is statistically no different between the two. So I can actually check that how good the fit is by checking that value. Right? If that value is very small, that means I'd have a bad fit. Being 1 means that I have an almost perfect fit. Okay, so that's what's, I think to answer your question, that's what's good enough. If you're doing desktop research, it's unlikely you're going to need it.
Oh, thank you.
This is about surveys, this is about people's perceptions.
It's not qualitative. Thank you, God.
Okay.
If you can go to the graphs that illustrate the raw data, the counts for the raw data.
Yeah.
So if you look at this, we can say the question on the right, more people agreed to the statement. Or let's look at the one where it changed drastically, because I think agreed still turned out to be the most. But the one on the left, disagreed was the most, right?
Yeah.
More people. So if you go to when it normalized it or optimized it, to the graph, that was normalized to be less. So practically, what does that mean?
Okay. I'll answer that now. Can you see that there's no way that we can work out an average of these? Okay? There's no such thing as an average or mean, because kind of what is the average? It's a category. There's no numbers on this. So you can't work out a mean. Would you agree with that?
Yeah, so it's just more or less.
No, that's fine. Okay. So if you put 1, 2, 3, 4, 5, that's an anomaly, because they're not numbers, they're words. So why? On what basis do you do that? Yep.
So Anthony, one of the slides before this, you showed a table with the responses, the actual responses from the survey.
Yep.
So what's wrong with just showing that in your research as
Right.
the responses? Like, could I just stop there?
Fine. You might want to stop there. All right? But if you then wanted to compare, what do people agree with? What do they disagree with? In this case, do executives, directors and non-executive directors see things differently? How are you going to do that? That's what I'm saying. This way you can do all of that. That's the point, is this way we can do the analysis. We can do the statistical tests. We can test to see whether there's a significant difference between males and females or between different areas. We can do a whole lot of additional analysis that you can't do unless you've done this properly. Okay, that's the answer.
Question regarding the question that's been asked here. Is it not a loaded question when you say internal audit used excessively? Because once you say excessively now, you're not sure if the person is agreeing with the comments itself or that it is excessive. I'm just trying to understand how the question has been asked.
Okay, I think the reason it's been asked that way was specifically to get the balance in the scale. You see, otherwise one tends to get, in fact we see it in this questionnaire, you tend to get people responding more positively. So by reverse framing that question, as we call it, right, we get the people using some of the disagrees and the strongly disagrees as well. So that's probably why it was worded in that way. Okay, probably. But I just want to answer the question now. I've got this, and yes, you can present it that way, and maybe if it's a simple descriptive study, that may be all that you're wanting to look at. Right.
So we can do it this way.
Yes, there's nothing wrong with that. What I'm saying is, if you want to do more with it, if you want to say, well, the average level, the average perceptions of the population, then you've got to take it further. Because so what? The 25 people said this or that. Don't we want to know more? Right. So this purely describes the sample. So if we look at this, all right, so what have we got there? We found that the mean of the one on the left is minus 0.45. The mean of the one on the right is 0.787. What that's saying is we've now got a scale of agreement. So the average level of agreement with this particular statement is positive. In other words, that it is above average level of agreement with that statement. That's what that means. This one is negative. That means that the level of agreement with this statement is below average because people are tending to disagree. In fact, if we look at it, the average is sitting within this neither category, actually. All right? It actually sits in the neither because the whole neither category is below average. So the average response across all of the questions is in fact sitting in the agree category. But there's something else that you can get, and that is that we can see that the spread of this one is 0.7, the standard deviation, whereas the spread of this one is 1.1. What that means is that there is more diversity of opinion about the second item and more unanimity or more consensus about this item. Now, there's no ways you're going to get that from your descriptive, your chart. You would not have picked that up from your description. So that's what we immediately are starting to see, a much richer picture of our statistics and of our data collection than we had. Okay, there's a SAS macro that'll do this for you. Okay, so you can do that as well. I've coded it into SAS if you want to. Okay, so yeah, which will do the rescaling and everything for you.
Like, I think the actual results, you had more on disagree and agree.
Yeah, so I'm interpreting the average and the standard deviation. I'm saying that on average, there's a level of disagreement with this statement compared to the overall average. So people are tending to disagree with this statement. They're tending to agree with this statement because of the positive mean. Have I answered that?
Yeah, look, I think, so the raw data did tend to have more people disagreeing with the statement.
So it's correct.
Yes.
Okay, but the difference is we've now quantified it accurately and precisely without there being any discretization error. That's the whole point, is that at no stage have we assumed a particular numeric value for any of these categories. That's the big difference, you see. That's the big difference. Okay? All right, so we don't have discretization error in this data set now.
So in other words, if you do this and we give you, I've interviewed so many people, give you the categories, you can give me this and give me just those two answers so that I know how to interpret.
That's exactly what you'll get, because you'll get that from the spreadsheet, because we'll look here, those two rows there are the two rows of the means and the standard deviations of each of the items.
Why is there 11.1?
That's just the numbering of the questions, that's all. That's just the numbers of the questions, there's nothing more than that. I could have labeled them question 1, 2, 3, 4, 5.
So at what point, which am I taking now? So you've got, for example, question 1.11, you've got those two answers, so 0. So am I going to interpret each one individually?
It depends on your problem statement. Depends on what you're trying to research. If you're just looking at the average level, then you'll just look at the means.
So I'll just
You'll just interpret the positives, the negatives, the significant ones. If you're wanting to interpret it to the next level, where you're looking at, let's say, the degree of consensus or diversity of opinion, then you might look at the standard deviations as well. You might be looking then further at, for example, if they're significantly above average or significantly below average. So there'll be a p-value there that we can interpret as well. Okay, so I can talk you through those. All right.
Can you?
Yeah, I'm not going to talk you through how important it is to your research findings. That you're going to have to work out. How?
I'm saying how.
H-A-U.
How?
I get caught out by that so often. I'm so sorry. And it's late in the evening. Come on, give us a break now, will you? All right. Okay.
Anthony,
Yes.
how do you then move from here to the graphs? I want to know how you move from this data to the graphs. Can you?
Which graphs? The ones I'm showing in the presentation?
Right.
I normally wouldn't expect you to produce that in your research. All I'm expecting you to do is to produce the means and the standard deviations, actually.
Okay.
That's what's important to me. I don't expect you to produce lots and lots of charts.
Because this helps analyze it better. If you have the graphs, you can actually see it and be able to analyze it.
Sure.
But from numbers alone.
Okay, you're obviously a visual person. If you want to, you can certainly produce those charts.
Is it possible?
Yeah, absolutely. It's not difficult. I mean, you just got to do a few tricks within Excel. Yeah, no, it's not a problem at all. If you were doing a traditional research report or thesis, we would expect it in an appendix. What I'm suggesting that for your submission, because it's a research article that's going intended for publication in a journal, probably not as an appendix, but probably as an additional supplementary file. So when you submit it onto Sakai, you just have it as a separate file and label it as such, so that the examiner can access it if they want to, but that it's not part of the actual 12 to 15,000 words that you're submitting as your article. Okay, so it's always accessible, but doesn't form part of the body of it. Okay. All right, so I wanted to show you that because it relates directly to the whole issue around the reliability and validity. This is the demonstrably a more reliable and valid way of analyzing your survey data. So it would be expected of you that you have this and as part of your analysis. As I say, as long as you understand it conceptually, you don't need to understand the mathematics of it. You honestly don't. But you need to remember that survey data does not, it's not numeric data generally when we're using these verbal scales. And the reason that I basically we're quite pedantic about it is because of the finding that one does get the incorrect answer to research if you don't do it properly, or you can get, not that you will get, but that you certainly can get the inappropriate, or incorrect, imprecise and inaccurate answers if you don't do it this way. All right. So I'm going to leave it at that. Next week we're going to look at, next session, which is on Friday, we're going to be looking at factor analysis and cluster analysis, which are some multivariate techniques, which is far more subjective. It produces very rich data. It's quantitative, and based on quite hectic maths. But fortunately, you don't have to know any of that. And then we're also going to be looking at a semi-quantitative technique called fuzzy cognitive mapping that I'll talk you through that. So that's what we're going to be doing on Friday. I'll see you then.
Thank you.
Thank you.
Okay. So you mentioned that the model just need to